Geometry lesson, proving lines are parallel. Okay guys, take a second or two to try this warm-ups. Pause the video please. Alright guys, so you should have gotten for the first one x equal to 10, and for the second one you should have gotten x equal to 5, and respectively the angle 1 for the first one is 60 and the angle 6 is 20. So the idea here was that we already know that if these two are parallel, right, then the corresponding angles are the same and the vertical angles are the same. By looking at that, we know that the alternate interior has to be the same, alternate exterior has to be the same. And because these are supplementary and they all have to be equal to each other, for similar reason, co-interior angles or same side interior angles has to be supplementary. We also notice that the same side exterior angle, co-exterior angle, has to be also, that's right, supplementary, because they're, dot and x are supplementary. We know that because those two form a linear pair. And also, if you have an alternate exterior angle, it is also congruent, right? Well, anyways, the information they gave here, 1 and 5 are corresponding angles. See that, guys? By corresponding angle theorem, they're equal to each other. Solving for it, x is 10. Plugging that back into the original equation, it's a 60 degrees. For similar reason, 4 and 6 are co-interior angles or same side interior angles, and they are supplementary, right? You could either say it or you could just give it a name, use the name that was given to you by the book. Me personally, I tend to just write it out as opposed to the name, because for me, like, different textbook uses different names, so I just prefer to do it this way. Anyways, in our textbook, I believe it's called same side interior angle theorem. Okay, so they're supplementary, they add up to 180, and then plug in the value for 4 and 6 and doing the basic algebra math, and then x turns out to be 5. Be sure to plug that back into the equation that we're looking for. We're looking for angle 6. Turns out to be 20. Now, what we're going to study today is called 4.3, proving the lines are parallel. We're basically going like inverse of what we learned. Okay? Sorry, converse, that's what I meant to say. When you switch P implies Q, if that's a direct statement, when you switch the order like this, Q implies P, it's called the converse. And that's exactly what we're doing over here, guys. The first one, of the ways to prove that two lines are parallel is that the converse of the same side interior angle postulate. All right. So, this book is calling it postulate. Okay. So, you know what? If you could tell me that it's the same side interior angle, postulate / theorem, I'll be okay. Because in a different textbook, some books will say the corresponding angles are postulates. Okay, and from that, everything else could be derived. Okay. So its definition is just written in reverse. If two lines are cut by a transversal, so that the pair of the same side interior angles are supplementary, then the lines are parallel. So that we switch the order in which this was written. And the converse of the alternate interior angle says, if the two lines are cut by a transversal so that the pair of the alternate interior angles are congruent, then the lines are parallel. So if alternate interior angles are congruent, then the lines are parallel. I mean the lines that were cut, that is, right? And then there's a converse of the corresponding angles. If two lines are cut by transversal so that any pair of the corresponding angles are congruent, then the lines are parallel. Okay, so that's why it's called different ways of proving that it's congruent. Okay. All right, guys. So let's move on to the next page. Let's do an example here, guys. Okay. So if you look at a quadrilateral shape, it looks like a parallelogram, doesn't it? And then we have something like that. You could use that as a mosaic. You could put a bunch of the parallelograms together and, make a tile out of it. Sometimes it's called tiling. So the idea here is that we have this shape right here. Oopsie, let's go with green, right? And if we make a copy of that over here, like this, I could make a whole bunch of copies of that and put it right next to each other. And then we could make a tile out of it. Like this. There's a reason why we could do that is because, right, this angle and this angle, right, if that's 120, that's a 60. They add up to 180, make a straight line, right? And this angle is 60, alternate interior angles, so we know that these two are parallel, right? It just fits nicely, doesn't it? All right. So that was a quick demonstration of where you could find all around us. So we're going to use the values that were marked, angle 1 and 2, and the lines 1 and 2. So how do we show that it's parallel? Okay, we are assuming that we are using these shapes, guys. For these exercise, we are copying this and popping it over here. So we have a line over here, here, and here. I don't know if that's clear from the way you drew. So the angle 1 here is what, guys? It's 120 degrees, right? And angle 2 is 60 degrees. What is the relationship between the two angles? They're same side interior angles, right? Right. If that's the case, what do we know if the same side interior angles are supplementary? They're at 180, right? So what is the conclusion? Well, since this right here, copy, paste, are supplementary, then, right, we know that the line 1 must be parallel to line 2, right? If the same side interior angles are supplementary, then these two lines have to be parallel. That's the conclusion, right? Good. So how about next one? What's angle 1 equal to in this case? Well, we're once again looking at this right here, guys, right? Angle 1 is a lower right. Lower right is 120. So that's clearly 120, and 2 is the same thing. They're both 120, right? So what is the value of that? That is 120, and 2 is 120. What is the relationship between angle 1 and 2? Not the value, but what is the relationship? Well, they're corresponding angles, right? Because in the intersection, the 1 represents the upper left, right? They're upper, these are lower, these two are left, these two are right. So that's upper left, and over here, that's upper left. If they're in the same relative position, it's called corresponding angles, right? Because they're congruent, so what's my conclusion? Well, if the corresponding angles are congruent, then we know that we have parallel lines. Therefore, lines 1 is parallel to line 2. That is my conclusion, guys. Okie dokie. All right, guys. So the next page, we really don't do this online. It's kind of hard to do it. I'll try to like verbally explain it to you, right? But let's go with the parallel postulate first. Through a point not on a line, there exists exactly one line parallel to that. What that literally means, right, is that if you have a line over here, guys, and there's a point over here, it's telling you that there's exactly one line across it like this. All right, but how do we find them? Well, if you had a compass, this is what you would do. So if you have a compass with you, try to follow along to my kind of verbal direction. Draw a line that goes through here, anywhere you like it is fine with me, okay? But make sure that they go through that. Now, this is what you do, okay? What I want you to do is open up a compass and draw an arc, just like that. And what you do at the same time, right, is make a copy of that and draw arc here as well. So before, that was the center. That's where you put the center of the circle, and you draw arc this way. And then using the same compass, you do the same thing, and this time put it on the P and draw arc the same exact way. Step number 2, what you want to do is you want to adjust the length of the what do you call that thing? I want you to adjust the length of the compass so that you start from here and here, and you want to make a length out of it, right? Measure from here to here. You see that? And then what you do is once you got that straight, and I want you to come over here and do the same exact thing right there. Okay. All right. Once you've done it, what I want you to do is draw a line, the final line, from here through this way. Okay. You have to go. Oopsie. You have to go through this point and this point. Well, I didn't do a good job of that, so let me change that. Okay. I should have brought that down just a tiny bit here. Something like that. Okay. And then if you draw a line straight through, it should come out parallel. Right? That's a little bit off, but if you had a piece of paper, right, that should come off. That's how you do a construction. But it's online is kind of hard. If we get back to class, when we get back to class, I can show it to you then. Okay. All right, but let's just move on though. All right. So that'll be like one quick construction. If we're in the classroom, we'll be taking care of that then. Using the angle pair relationship, verify the lines are parallel. Well, is that true? If angle 3 and 5 are congruent, well, it says identify. Well, they're alternate angles, aren't they? This one and this one. So this is a alternate interior angles congruent. And then, yes, but are they parallel? Of course they are. Because of converse of alternate interior angle theorem. All right, part B. If angle 4 is blah blah blah, that's not as important right now. And then angle 8. What is the relationship? Oh, they're corresponding angles, right? It means they're the same. What is the so angle 4 and angle 8 are corresponding angles. Are they parallel? Well, I don't know. Are they the same? Okay. Angle 4, according to this, is x plus 20. X is 15 though, isn't it? Plug in for 15. That's 35 degrees. Angle 8 is 2x plus 5. That's twice the 15 plus 5. That's 35. Oh, they're equal to each other, right? Yes. Because, so here we go. Angle 4 is equal to angle 8 by substitution property, or we could say transitive property, right? So they're congruent, or we could say they're congruent, right? If they have the same measurement. All right. Are they parallel? Yes, because of the converse of corresponding angle theorem. Because the corresponding angles are congruent, that means that lines that are cut by transversal must be congruent. All right, guys. So this is the your turn portion of this particular lesson. Why don't you pause the video and try this on your own. Okay, guys. So here's the answer that you should have gotten. Number 7, that's the trace mark that I should have seen right here, right? And then number 8 and 9. Okay. Please note that this is the homework. Make sure you print it out. This lesson goes on actually to 4.4 as well. So right here, we have a perpendicular lines. Okie dokie. All right, so there is a warm-up, but we're going to do that when we go in class. Okay, so take a look at it. Now, once again, this right here is more of the stuff that what we would do in class. So you will follow direction step by step by step, right? And it will tell you how to do a perpendicular bisector. So in a classroom situation, you will literally sit there and do this with your mates. Okay. All right, guys. So let's do more of pencil and paper type of work. So we're gonna do a quick proof, guys. But before we do, let's figure out what that theorem that we're trying to prove. This is what's called a perpendicular bisector theorem. Anytime we give it a name, it's important. All right. So here we go. If a point on the perpendicular bisector of a segment, okay, a point on the perpendicular bisector of a segment is on the perpendicular bisector, sorry about that, then it is equidistant from the endpoint of the segment. Oh, so this thing is same distance from here to here. Why is that? All right, but before I begin though, right, I'd like to draw things out a little bit if you don't mind. Okay, first of all, if I draw a line over this way and this way, doesn't it create two triangles? Okay, the fact that it's perpendicular bisector tells me that these two are the same. Okay, let's call this, I don't know, let's give it a name M because it's the midpoint. So MP is equal to itself. And they're both 90 degrees. So these two things are equal to each other, right? Oh, by side angle side theorem, they must be equal to each other. Another way to think about that, right, is that if I tried a Pythagorean theorem, okay, if I knew this length and this length and this length, right, and these two are the same, I could use Pythagorean theorem because the numbers will be the same. Just give it a name. What if this is 3 and these are 4? Would they both come to 5 if you did Pythagorean theorem? Yeah. So you could think of it that way. Okay? All right. Just give me a second. And why don't you pause the video and try to write out the theorem yourself, and we'll continue. All right, guys. I hope you had a chance to work it out yourself. So I wrote it out for you guys. So the way this will be described is that we would actually always write down the given, which I did. And then I'm going to start with PA right there, guys, okay? Well, I'm going to include that in this whole argument. We know that it's perpendicular bisector. So we're going to say that because it was given to us that the AM and BM are equal to each other. That's the definition of a bisector. And we know that the PMB and PMA are both right triangles. That is the definition of the perpendicular lines. Remember, this is a perpendicular bisector. So what that means is that these two are equal to each other, this angle and this angle, because they're both right angles. Definition of the right angles, or right angles are congruent to each other, right? Well, actually, it's not a definition of the right angle, is it? Right? The right angle has the same measurements, so we could say that the right angles are congruent. And we know that PM and PM are congruent to each other. That's reflexive property. Now, if you think about this length and this length matches with that length and that length, and we have an angle in the middle. So that is a side angle side. So the angle PMB and PMA are congruent to each other by side angle side triangle congruence theorem, right? And because of that, the PA and PB are equal to each other through CP/CTC. If they are congruent, they have the same measurement. That's definition of congruence. And that is how you would go about proving this thing. All right, guys? Okay, the next page. We have a converse of the perpendicular bisector theorem. That is to say that if a point is equidistant from endpoints of the segment, then it lies on a perpendicular bisector of the segment. Yes? Okay. The way we would argue this, right, is what we call a proof by contradiction. Okay? But we're given that PA and PB are congruent. And then P therefore has to be perpendicular bisector. But let us suppose that we're going to start with the P is not perpendicular bisector, right? Let us suppose that for a second. Okay. All right. So one of the things we could do is, before we get started, if that's true, we know that the PA squared has to be PB squared, right? All right. So we're going to do this by proof by contradiction. Okay. So we're going to start with the fact that P is not on a perpendicular bisector. Okay. But using the given information, right? Let's start with the fact that APQ and BBQ, triangle BBQ, BPQ are right triangles, right? So this one and this one right there, okay? So by Pythagorean theorem, we know that the AP squared is equal to PQ squared plus AQ squared. And we know that the BP squared is equal to PQ squared plus BQ squared, right? In other words, this squared is equal to the sum of this and this squared. And same thing over here, guys, right? Now, if that's the case, then by transitive property, because we know these two are equal to each other, if they're equal to each other, square of them should equal to each other. So we know that the PA, right here, PB squared is the same. By substitution or by transitive property, right? I'm going to go with transitive property, but you could say substitution if you like. Transitive property, because these two are the same, means these two has to be the same, right? So we know that the PQ squared plus AQ squared is equal to PQ squared plus BQ squared, and we know that these two are the same, right? So by subtraction property, that implies that the AQ squared is equal to BQ squared. By square rooting both sides, we know that AQ is equal to BQ. Now, isn't that a contradiction? Because we started with the fact that P is not on a perpendicular bisector, which means QP cannot be a perpendicular bisector, which means that AQ and BQ cannot be the same. But we just proved that, didn't we? That's a contradiction right there. Because they're a contradiction, we say that whatever our assumption is false, right? So because there's a contradiction, the assumption is false. Therefore, opposite must be true. Therefore, P is on the perpendicular bisector theorem. Okay, guys? Once again, this whole thing was called indirect proof, aka proof by contradiction, and there's the procedures. You should take a look at it, but that's what I did. Okay, guys, so we have the next page. Why don't you give it a shot? Okay, this right here should be perpendicular, means that two figures are perpendicular, right? Meaning that the way we would say that, for example, line L and M are perpendicular, or X, Y, and AB are perpendicular. Using that information, why don't you guys try to fill this out? I'll pause the video and let's go over it together, okay, guys? So we continue. Knowing this information, guys, how were you able to do these? Okay. Now, what should have happened is that when something is perpendicular like this, you know that it's 90 degrees over here, right? So if a perpendicular, if two lines intersect to form a right angle, then they are perpendicular, and they intersect to form 90 degrees. So how do I prove that? Well, let us say that this is 90. Okay, because what they're saying, they form one right angle. Then how do you know that the rest are all right angles? Well, what we know is that angle 1 and 2 are linear pairs, so they add up to 180, linear pair. And then substitute angle 1 for 90 and solve for 2, you get 90 degrees. And you do the same thing, but what you could do is, you know that angle 1 and 4 are vertical angles, so they're congruent to each other, check. And 2 and 3 are vertical angles, so they're the same, but 2 is 90. So that says if one angle is a right angle, all 4 has to be the right angle. Therefore, in the definition, you only have to say that it forms one right angle, because it means that all 4 angles are right angles, right? The part B is if 2 intersecting lines form a linear pair with unequal measure, then the lines are perpendicular. Say what? Okay, in this particular case, it says equal measure, right? So we got angle 1 and 2, they're a linear pair. If they're equal to each other, then they have to add up to 1 and 2. But I can substitute 2 for 1 because they're equal to each other, right? And then what we end up with twice the m, a measure of the 1. So divide 2 to both sides, measure 1 is 90. So that's 90 degrees. Therefore, when 2 lines intersect so that you get a right angle, we say they're perpendicular. So that's the conclusion that we have. Okay, guys. So that is it. So this is your turn. So do me a huge favor, guys. Pause the video. Okay. I'm going to assume that you're done, guys. So this is the answers that you should have gotten. So here we go. And that's the last one. Alright, guys. With any questions, we'll discuss it in class. Okay, guys. See you tomorrow.